I just want to remind you, it's super important what we just did because you may not believe me. It doesn't really matter whether you believe me or not. This is what experimental evidence continues to shows us. And is it uncomfortable? Yeah, I think so. That's not my problem. That's your problem. I already have my own uncomfortableness with the material already. And I can guarantee you that I've been doing it for a lot more years than you guys have. And yes, I struggle with it. Okay. So just so you know, I also struggle with it. So what I want to do here is that I want to start going over the stuff that we were talking about. Okay. So what we were dealing with is that we were dealing with Einstein's puzzle, right? And the light puzzle that he had was that if you were to chase a light wave and you traveled at the same speed as the light wave, you would see stationary light. So they're saying here is that if one was in a frame of reference at light speed, then that tells you that you would see stationary light. And if you see stationary light, in some sense, you could sort of like reach out and grab some of this stationary light. And that was the puzzle that Einstein, kept trying to look at. But the problem with this here is that there's no stationary light solution for Maxwell's equations. So Einstein knew that there was a problem someplace. He just didn't understand. It turned out that he needed more physics to really actually get a sense of that. And I think we talked about this already last time, but as a sake of review here, so to give you a sense of what this actually means here, is that I'll take a Newtonian viewpoint, which is exactly what Einstein had. So you could imagine that I have in this case, I'll call her Maria. And Maria can really throw a baseball. So she could throw a baseball that could travel 100 miles per hour. Okay. So she throws this baseball relative to what? The earth, of course. And then we have a second scenario here where there's a car that could also travel at 100 miles an hour. So in this frame here, we'll say that this is Juan. So in this scenario here, this car is also traveling at 100 miles an hour. So if it was just set up just right, you could imagine that these guys sort of like start from the origin at the same time. That means Juan is passing through the origin as Maria accelerates the ball to 100 miles an hour very, very quickly so that they're traveling at 100 miles an hour. So from Juan's viewpoint, what you're seeing here is that you see a stationary baseball. If they're traveling right next to each other, Juan looks out and sees that this is a stationary baseball, so he should be able to go out there and sort of like pluck it. Okay. So as he plucks it, that's what I mean that, he just sort of like picks it off. And that's what Einstein is referring to, that if you chase a beam of light and you went at light speed in your frame of reference, then you should see stationary light. But as I said already, he knew that there was no stationary solution for Maxwell's equations. So he knew there was a problem. So if you look at the history of all of this, here's what you find. What you find here is that somewhere around in 1905, so in 1905, Einstein got the key insight. And within 5 weeks, published special relativity. Okay, after getting that key insight. And here's some of the key points. So there's really 2 key points here. So Einstein, he claims 2 key points. The first point, which I think is super important here, is that he says that he declares that there is no ether. And note, this is shocking. Why is it shocking? Again, imagine what? Water waves without water. That's what Einstein is saying there. But there's a reason why he says that. And the question is, why? So when you look at Maxwell's equations, what you find here is Maxwell's equations do not invoke a medium for wave motion. And because it doesn't evoke a medium for wave motion, he implies then that it does, so that light does not require a medium in order to travel. It's a lone traveler. And this piece is what I consider super hard. Okay, so I think this is a very hard conceptual point here. And this is the one that always bothers me. And so what he says here is he says, Maxwell's equations do not invoke any particular frame of reference for light. Okay, so since Maxwell's equations do not invoke any frame of reference, then what that means here is that then the speed of light is relative to anything and everything. Okay, and this is really the key point. relative to anything and everything. Of course, we still mean inertial, but he's saying that if we're talking about inertial frames of reference, this speed of light, c, is a constant for all inertial observers. And I think that's the hard thing right there. This is the most disturbing thing about what Einstein said in special relativity. And I'll explain this in a minute here, why that is so tough here. So then the second thing he says is he says this. So Einstein resolves the dichotomy between Newtonian versus Maxwellian physics. And what he says here is that he essentially says that all physics is invariant for all inertial observers. And this is really what he calls his first postulate. I'll say it here in a slightly different way. So for the first time, when it says all, it says it now includes Maxwell's equations. Before, it was only Newtonian physics, and people didn't know whether it was Maxwell's equations or not. But now it includes it. And that's what's called, so in a modern language, this is what they call the principle of special relativity. So what's special? Really what's special here is that it includes Maxwell's. That's what's special about it. And I know a lot of times when people say, no, special means constant velocity. Well, yeah, of course it does, because we said inertial observers. So if you say inertial observers, then we're talking about rest or constant velocity, of course. And so what does it say here? It says that all the laws of physics are the same for all inertial observers. So we really, seems like we didn't go very far, right? We didn't go very far. All we went was from Galilean, we swapped out Galilean, put in special, and then just said all the laws of physics. It looks like we haven't done anything. And here's where that's not true. This thing about the speed of light being a constant is super disturbing. I mean, for common sense. And that's what I want to get at. But before I actually, say anything further here, 115 years ago, when Einstein developed his principle of special relativity, things were not so easy. So what he did here is he actually broke the principle of special relativity into two pieces. He called postulate 1 the principle of special relativity, which is exactly what's written here. Then he wrote a second postulate, and that second postulate says that the speed of light in a vacuum is always equal to c, and it's independent of the motion of the source. Now note, that's kind of a redundant statement. The reason why that's a redundant statement is that when you say all the laws of physics, which includes Maxwell's equations say that the speed of light in vacuum is always c for all inertial observers. So it's a redundancy in that thing. But like I said, things were not so simple back then. So now, what we really got to get to is that now we need to do the interpretation of c being a constant. C being a constant. That's what we really gotta get this. Now, one of the things here, before I actually get into the details about this, I want to give you an analogy first. Now, this analogy is a Newtonian viewpoint and makes common sense. Okay. Now, one of the things that we can do here is that we could imagine that we have two locations. We have this location, which is Santa Cruz. And then I have another location, which is San Francisco, which I'll just call SF. Now, you could imagine here that we have two people. Okay, so we have two observers. And for the sake of argument, I'll call them Ollie and Riwa. And so we talk to Ollie and Riwa, and they all, and what they do here is that we ask them, how far apart are these two cities? Well, you probably Google it, or you probably know already, but I'm going to guess it's around 75 miles. So according to a Newtonian viewpoint, we come in here and we just say, okay, so the distance that Ollie claims is 75 miles. And the distance that Riwa claims is also 75. So these observers are saying like, yeah, it's about 75 miles. And then you get into a car and you drive this thing and you ask, how much time does it take to go? So then we ask about, what about the time duration of the trip? And they're probably going to say, I don't know, maybe 75 miles takes, I don't know, an hour and let's say 20 minutes. So when they measure their times, or they claim that this is how long it's going to take, I mean, I think everybody is going to say, well, yeah, that's more or less correct. And what this example tells us here is that that a Newtonian viewpoint measures distances and time durations as absolute quantities. So if they were to ask me how far those two distances are, I'm going to say 75 miles. If I was in a car, I'm going to say, yeah, it's going to take me about an hour 15 to an hour and a half. And we all agree on that. This is common sense. And I'm saying that that's not correct. That common sense gets in the way. And before I move on to trying to explain this thing, I want to do one more thing here. And this is something that I've done very similar beforehand, but I want to keep going with this common sense notion here. Now you could imagine that I have, again, two observers this time. So in this case here, I'm going to use some generic names. And this is who I'm going to call Maria. And we could call her being in the S frame. And what do I mean by the S frame? She is at rest relative to Earth. And then there's Juan. So Juan, of course, is in the green car, and we're going to call that frame the S prime frame. And what do we know about Juan? Well, Juan is driving 80 miles an hour, let's say. And while he's sitting in his car here, we know that in his frame of reference here, he is moving, how? He's moving 80 miles an hour relative to Earth. That's what I mean by this S prime frame. So he's moving 80 miles relative to Maria, and Maria is moving 80 miles relative to Juan. I can't say, right? There's no preferred frame of reference. No one can say with special relativity or Galilean relativity that I'm at rest and you're moving. You can equally say, no, I'm at rest and they're moving. And we've talked about that to some degree. And we've already talked about this, but we could imagine here that Maria has a really good arm and can throw the ball 100 miles an hour. So here we go. So Juan car goes 80 miles an hour. What does he see? Okay, so note this speed that Maria throws the baseball is at 100 miles an hour. So what is Juan going to see? Common sense, as we've already talked about this before, tells us that he should see the speed of the ball going by him at 20 miles an hour. That makes common sense. Now, so I would say that this is common sense. What is not common sense is Juan claiming he saw the baseball moving at 100 miles per hour. Right? This is not common sense. You would be shocked if he says, no, it's moving 100 miles an hour relative to me, even though his car is going 80 miles an hour. And you should be even more shocked now if Juan comes back and then takes off at 99.9 miles per hour. What's common sense? That Juan would see the baseball moving at 0.1 miles an hour, right? That's common sense. If Juan comes back and then says, no, the ball moves at 100 miles an hour relative to the car. If one came back and said this, clearly this is not common sense. So as a consequence, when you look at special relativity, so when you look at the principle, Einstein, when we take this to light, when he says Maxwell's equations predict C equal to a constant for all observers, period. Of course, inertial observers. When he says that, whether you realize it or not, but this statement right here, that is the crux. And what I mean by the crux in this situation, that means that something completely, there's like a whole new fundamental thing. So this implies that something completely fundamental is different. Something completely fundamental is different about that as soon as you say that the speed of light is constant for all observers. And I love this analogy that I started saying probably 40 years ago, 30 years ago. And this analogy, I call it my jungle analogy. And it goes something like this. And it says something like, you're going through the Amazon jungle and you come into a village and you find out that the natives live to an age of, let's say, 400 years. If they live up to 400 years, what does that tell you? So if their age is equal to 400 years, that tells you something is completely new. There's a new type of biology. Oh God, I think this is the way you spell biology. There's some type of new biology that is occurring. This is what this means here. C equal to a constant is exactly the same thing. There's something fundamentally different. And it took an Einstein to figure this out. Even though it was in the face of many people, it was Einstein that really figured it out for the first time. And this is what he said here. What he says here is that if the speed of light is equal to a constant, and we are in an inertial frame of reference, what does that mean? Well, come on. How complicated is it to write constant velocity equation? It's distance over time. Einstein says that if Maxwell's equations predict the speed of light to be constant, the only conclusion then are observations of distance and time is different. And my favorite way to write this here is that I can write constant equations two different ways. I could write them with a big D or, so what I typically say here is that as long as this ratio is the same, then I can write this proportionality with any size quantity that I want. And so this is what Einstein says by looking at this really simple thing. Why? Because it's constant velocity. You don't get any things like this. So he goes like this. The only way that two observers, okay, two observers like who? Maria and Juan can measure C equal to a constant is if Maria's and Juan's distance and time measurements are different. That these two time measurements are different. So if I look at the distance that Maria measures, it's not the same as Juan's. And the time measurements between Maria and Juan's are not the same. They are not the same. This is one of the big realizations. This is what Einstein, you needed an Einstein to show us this. So if I go back to the previous statement that I made, so I'm going to screen to a previous thing here. And the question that I asked was this. If we had a trip from Santa Cruz to San Francisco, if you said that your measurement was 75 miles in special relativity, that's not true. Ollie and Rewa would have different distance measurements. They would have different time measurements. It depends on your frame of reference. So here's the crazy thing, right? And I think this is really hard to perceive here, is that if two inertial observers, actually it doesn't even have to be inertial, if two observers measure different quantities, then they have no objective reality. Let me say that one more time because that's going to take some time to sink in. If two observers measure two different things, then that quantity has no objective reality. So distance measurements have no objective reality. Time measurements don't have no objective reality because different observers can measure different times. And this is a result of having the speed of light to be constant. And I think that is a brutal thing. Okay? I don't think that's an easy thing. I think that's a deep, deep thing. And I cannot even tell you how hard this statement is for me. And what I mean by that, I'm going to be jumping the gun here a moment, but I think just to show you what I mean, how even I am not RC when it comes to this. So many years ago, I worked at a place called SLAC, the Stanford Linear Accelerator Center. And they have a building. And that building is 2 miles long. So what I would do at lunch is that I would go running and I would pass by this the accelerator. It's this if you ever drive over 280 by Sand Hill, you'll see that. And that used to be part of my path where then I would go into some of the fields owned by Stanford, which you could go and run in. Now, I would say that that building is 2 miles long. So the distance that Carlos would say is 2 miles. On the other hand, you have an electron now. They would shoot these electrons down the beam. And and you'd ask me, so how far did the electrons travel? Well, I would say they traveled 2 miles. But that's not RC. I'm not being relativistically correct. This is Carlos's frame of reference. But in the frame of the electron sees the accelerator only 3 feet. So in the frame of the electron, how long is the accelerator? It's 3 feet. So as I'm going along, I'm going like, no, this is 2 miles. But even though I have years of experience, I would go by this and kind of chuckle and go like, there's no goddamn way that accelerator is 3 feet long. It's like I'm saying that my frame, Carlos's frame of reference, is the preferred frame. It's not the electrons. I'm the preferred frame. But we already know from Galilean relativity that you can't tell the difference between being at rest and constant velocity. So if I look at the laws of physics in Carlos's frame, they're valid. If I look at the laws of physics in the electron's frame, they're valid. But because we both make different measurements, in other words, because this is not true, they're not the same but different, then me saying that the accelerator is 2 miles or the electron saying that the accelerator is 3 feet has no objective reality. Two different observers measure different distances. Distance is in the eye of the beholder.
So isn't that kind of like saying you could go even slower than you jogging around the perimeter of the building and then make it even longer? You could make it 4 miles long by being an ant and going slowly, I mean.
Sure. I mean, it depends on your relative frame of reference, right? Your frame of reference will determine what that distance is. So the observer, whatever the inertial observer is, they measure different distances. So for you to say, this is how far something is, you're being relativistically incorrect. You are not RC. You cannot make that statement.
But isn't there an objective maximum length? Like you can contract space.
Wait. If there's no relative distance, there's no relative motion between you and another observer, then there's something called a proper length. However, somehow if somebody's moving relative to you two guys, it's almost like you're saying, well, my distance is right. Or like you said, there's a maximum distance. You mean the proper, where that thing is at rest relative to you. But I mean, it kind of, but you gotta
But
admit,
isn't that objective?
no,
I can't
because
use a measuring tape in the rest frame of the Slack building and say that this is objectively 2 miles long.
so, but then you're saying that your being at rest relative to that frame is the right frame.
Uh-huh.
And you can't do that. That's what I'm saying. I'm chuckling as I go along. And by the way, I was there for 7 years at Slack. And I would chuckle. I can't tell you how many times and go like, there's no, okay, excuse my language. There's no fucking way that that thing is 3 feet. That thing is 2 miles long. I just ran past this thing. There's no way that's true. And in my head, I'm going like, damn, dude, you're being so not RC. You got to be relativistically correct. And I get caught in these conundrums every now and then. But remember what I said. This is the most battle-tested theory ever. This is more tested than Newton's laws. And if you were in the electron's frame and you didn't set up the distances right, what would happen? You would never get the electrons to go all the way to the detector. Never. That's a hard concept to grasp. And so the way to get a sense of what I mean by this picture here, and I kid you not, this picture up here is one of my most favorite pictures. That C is small distance over big time is the same as big distance over big time. So I really want to interpret that one more time. So I want to interpret C equals to distance and big distance over big time. And the way I write this mathematically is that I typically write it this way. And the unprime, so the unprime slash prime frames of reference are arbitrary, okay? So if they're arbitrary, it doesn't matter. Ooh, I didn't write that right. It's okay. It doesn't matter which I call unprime or prime. And so the way we typically try to get our handle on this scenario here, which is what it's called a light clock. And what a light clock does here, it essentially does the following thing. You could imagine that I have sort of like an elevator or a freight car, however you want to think about it. And you have two things. This guy's the emitter of a light pulse, and this guy's the detector of the light pulse. So what happens here is that the light goes up, and once it gets up to the top here, you have a mirror. Now we have a perfect mirror, Jason, not that 96.4% shit. And so then what happens here, this is a perfect mirror. There's no absorption of light. There's all of the light going in is the one that's coming back out. So what you're finding here is that there's a tick, and then there's a tock. So when a light clock goes tick tock, it goes all the way up and it comes all the way back down. So you capture this. So now Here we go. So if you are in the frame, okay, so in this frame here, let's say that I have Juan at rest relative to the earth. And he can't be in moving things, so we put Maria into this clock here. Okay, and so when we look at Maria, Maria's frame, what you're seeing here in this prime frame versus this S frame, what I'm seeing here is that there's no motion between them. So now, if I have my source here and I have my detector, this clock, so then it goes in and it goes, and what I'm seeing here is that if these two clocks are at rest relative to each other, they're going to cover a smaller distance between the tick and the tock. So if I look at this thing here, if I look at the speed of light, since the speed of light has to be a constant, if I have a small distance, right? So this would be a small distance between tick and tock. The only way I could have that is if it occurs over a smaller time duration. But now I have a different scenario here. What I have here is that now there's relative motion between them. If there's relative motion between them, you could imagine that I now have the following scenario here. I have this guy moving with some relative speed, and then it comes all the way over to here. So what I'm seeing here is that if I now look at these two frames, so now I have an S prime frame that's moving V relative to an S frame. And what do I know about this S frame? It's at rest relative to the earth. The S prime frame with Maria is moving. So when I go and I look at Maria here, she's right there. She's right there. And so what you're seeing here is that you could imagine now that here's my source of light. So what's going to happen? As it moves, it's traveling what? A farther distance in order to go from the tick to the tock. So all of a sudden, the distance of travel between here is now larger. So when I look at the speed of light now, if this distance is bigger, come on, I don't know what's going on. If this distance is larger, I have no other way than to say that I have to have a bigger time here. So what this is saying here is that larger distance measurements require larger time durations between tick and tock. So when I look at this equation here, each observer measures different distances and different times. So each observer measures different distances and times. And I don't remember who I heard this from, but I love the saying. It says that it's in the eye of the beholder. So for observer that are at rest relative to each other, they measure a particular distance and time relative to their eye. As soon as one frame is moving relative to the other, they measure different and time intervals. So in this case here, Maria is at rest relative to the light clock. So she sees smaller distances and times as well as Juan. But as soon as Maria is moving relative to Juan, Juan sees a bigger distance and a bigger time difference between the two events. It's
Yeah.
all in the eye of the beholder. Yes.
So does that mean that Maria measures, like does the same measurements in either scenario?
In each scenario, she measures the same distances and times because she is at rest relative to the light clock.
Okay, thanks.
Now, the thing about it is that this theory has been tested so much, like I've said before, the experimental evidence is shockingly strong. But probably the coolest experiment that I've seen was done back, I think it was done very, very early on, like in the mid 70s. And then they redid it to higher precision in the 1980s. And this was the experimental evidence of this thing here. And what they did here is that they had two electrons and a positron colliding with each other. Okay. And what they did here, I'm sorry, what I said was incorrect. Okay. I got to go back and change this. So this evidence of C being a constant is what I'm really talking about. And so what they did here is that they produced a particle in a collision, and I won't do the collision just because it's too complicated. So you could imagine that you have this thing called a pion. So this is a neutral pion. And this pion had a speed of 0.9998, the speed of light. Okay. And then what happened here is that the pion is unstable. So this pion is going along this part of the detector. So you could imagine that, let's say this is the pion, and it's moving in this direction. At this point right here, okay, at this point, I'm going to say that the pion decays. And guess what it decays into? It decays into 2 photons. What are photons? They're particles of light. Right? I really can't say that, but it's okay. And here's what happens. This pion is moving at almost the speed of light. So then it sends, to conserve linear momentum, it sets 1 photon in that direction, and it sends the other one backwards. And this is only to conserve momentum. And then what did they have? They had 2 detectors right here. And these detectors here measured the speed of photons. You know what they measured? Each photon had a speed of c. Each photon was measured at speed c. Even though the pion was moving at 0.9998 c, the photon going in the forward direction measured c. The photon going in the backward direction measured c. That is shocking right there. So what we want to do now is that we want to now start heading towards moving from Galilean relativity to Lorentz relativity. In other words, we need to look at the transformations. By the way, just to make sure that we're clear, right? What's common sense here? So if I label this as photon 1 and this one as photon 2, common sense tells us what? That the speed should have been c plus v, so it should have been roughly 2c. What happened? Not true. It was c. Common sense tells you what? That this should have been c minus v, so it should have been roughly 0. That's what common sense tells you. That's not true. That's not what was observed. So now I want to get into a little bit of the mathematics and not really derive anything, but I want to talk about something called Lorentz transformations. So what I want to do is that I want to remind you that we dealt with Galilean relativity and transformations. It is the mathematics of these transformations that tell us what's actually happening. And even though we talked about this before, I just want to summarize this here. So in summary, if you're boosting from S, and what we said this here, this is at rest relative to Earth, and now you want to boost into a second frame, S prime, which is moving relative to Earth. So note that I didn't put relative to Earth. I should. And when we looked at these transformations, what we saw is that from a coordinate transformation, that that this is, I'm boosting from here to there. Right? That was the boost from the rest frame into the moving frame. And then the other thing that we said here is that time in one frame was the same for all frames of reference. And this tells us absolute time. And we could do it the other way too here. We can boost from the prime frame to the rest frame, right? So this was the moving frame relative to Earth, and then I can boost to go into the frame that's at rest relative to Earth. And then we had two equations again, which said that it looks like this and it looks like that. So what we need here is that we need to modify. So these transformations must be modified to keep C equal to a constant in all frames of reference. Okay? In all frames of reference. So what we want to do then is that when you modify these things, these new transformations are known as Lorentz transformations or a Lorentz boost. So most physicists in the know don't call them transformations, they call them a boost, even though in the textbook they call them a transformation. So here's what you find here. So these new boosts read like this. What they read here is that if you're going from the S to the S prime frame, you get that X prime is equal to gamma times the quantity X minus VT. Okay, so what you're seeing here is that if I compare the Galilean one up here to the Lorentz one, you could see that there's this new gamma factor here. But that's only part of the thing here. So before, with the Galilean, you had a mixture of what? Position and time. So they had position and time mixed together. Now, if you look at the Galilean one up here, you could see that there's no time mixing with distance. That's not true in the Lorentz transformations here, or boost. Here's what you find. You find that time now has been altered. And it's altered by mixing time and space together to get you this equation right here. So you're seeing a mixture of time and position with time here. Okay, so again, this is from what? Rest to moving relative to Earth. And that's one of the Lorentz transformations right there. And so automatically, this is telling us that I have different distance measurement because it depends on this gamma. And I haven't talked about gamma here, but I will right here real soon. And then time is different. So when we go back to this picture up here, look at my picture right here, right? This is my picture right here. So if I take that picture and I bring it all the way down, let me see if I can just pop that in. This is what you're seeing. The observer at rest relative to the light clock is going to see different distances and time measurements. okay, where there's this thing called gamma, which is a relativistic factor. And this relativistic factor is 1 minus v squared c squared square root. But more than ever, people, or especially me, I'll call that ratio beta, which is v over c. This is another super important equation. Okay, so that's how I boost from one frame into another. Now to boost back, I essentially got to do what? I got to come back and put the plus or minus sign. So if I boost the other way, where I'm going from the prime frame to the rest frame relative to Earth, then I just replace these guys. But this time I change out the primes and the plus sign, and then the time is going to be the same thing, but I get a plus sign this time. Like that. So that's another of these boosts here. So my job now is to really interpret what these two equations are. Okay? My job is to interpret what those two things. And what you're going to find here is that there's two things that we'll deal with. So two things are what are called time dilation and length contraction. And these guys are literally embedded in these two Lorentz transformations. So the way you get this thing called time dilation and length contraction is that these two are embedded in the Lorentz transformations or the Lorentz boosts. They're there. That's how Einstein figured out that it was about the time and length measurements that, you end up getting this thing. So here's what I got to do. I got to go in and I got to start looking at these two things. And you're going to see that these equations are really deceitful. Why are they deceitful? Because if you look at the textbook sort of like gives you a little white lie on how you use these Lorentz boost equations. And it's actually, they're really not RC when they actually say these things. But what we're going to do here is that we're not interested in single position measurements. We're interested in changes in measurements. That's the most important thing. Okay? So one of the things that I want to say before I get right into that is that I want to do this here. When I think about the principle of relativity, all I know is this, right? So the principle of special relativity implies, of course, that C is always equal to a constant for all observers. And one of the things that I said here is that instead of drawing those big distance, little distance type things here, I'm going to start to use these guys. Because mathematically, this is where we got to go. So what you see here is that the Lorentz boosts mix up space and time together. Okay? They mix space and time together. And what ends up happening is that there's something new. It's not space and time like we knew before, where we could separate them. When they're mixed together, is that you cannot ever separate them. Ever. And so what we do here is that we call this something different now. It's called space-time. So when I write C equal to delta x, delta t, or delta x prime, delta t prime, what I'm really saying here is this, that space and time intervals will adjust themselves. In other words, they're going to be compensating themselves to keep C equal to a constant. And they do this exactly, okay? They do this exactly. So space and time will adjust themselves to always keep C equal to a constant. So when I say space and time intervals, I mean space-time. Space-time will adjust itself to keep the speed of light equal to a constant. So here we go. So now we then start dealing with time dilation. So the first thing I want to do is I want to start talking about time dilation. And we always have to worry about two different frames of reference. So you gotta be really careful here. So we always use two different frames of references. So what I'm going to do here is that I'm going to imagine here that I have Juan here. So Juan is at rest relative to Earth. And he's always there. And in this frame here, I'm going to call that the S frame. Now, the next thing that I'm going to have is that I'm going to have a rocket ship. And with this rocket ship, I'm going to do in green because this is where Maria is standing in this rocket ship right here. So this is Maria, and all I know is in this frame, I'm going to call that the S frame, and all I know is that she is moving at constant velocity. We'll talk about acceleration in a little bit, but we're always wanting to compare these frames of reference here. So now, what actually happens here? If Maria and Juan are in the same inertial frame, they measure the same delta x's and delta times because there's no motion between them. If there's no motion between them, then that's it. So I should be careful. That means that they have no relative motion between them. It's when they have relative motion. That's important now. So then the next step here is that now there is relative motion between them. So remember what relativity says here. There's no preferred frame of reference, right? No preferred frame of reference. So it's common to say the following thing here. Well, here's Juan, right? Juan is standing in his frame, and then Juan says, no, it's Maria that's moving, right? Relative to him, Maria is moving at a constant speed. So when I look at Maria here, you know, from Juan's viewpoint, he is at rest. Maria is moving. So because there's relative motion between these two, then the distance measurements between them are not the same, and the time measurements between them are not the same either. And so Juan cannot say, right? Juan can't claim he is at rest and Maria is moving. Right? There's no preferred frame. So what happens from Maria's viewpoint? Well, from Maria's viewpoint, she's stationary. Right? She is stationary. So as she's stationary, she's sitting right here. And it's Juan who's actually moving away at a constant speed. So in this frame of reference, these guys do not measure the same space and time measurements. No one can claim that their frame is the preferred frame in order to make measurements. So Maria can claim or can't claim that she is at rest and Juan is moving. That would be not RC. The only thing that you can claim here is that relative to the earth, Juan is at rest. Maria is moving relative to the earth, and therefore her time measurements and space-time or space measurements will be different than mine. But equally valid is Maria's viewpoint. She could say that the light clock is at rest relative to the rocket. So my light clock, compared to Juan's measurement of my light clock, is going to be different. Either way, people can both claim that space and time measurements are not the same.